Hi there. In the last episode, we coded a disk benchmark tool, which allows us to measure the write speed of a disk that you're on in megabytes per second. And in this episode, I want to improve this code a bit because, as you can see, it's quite monolithic. So this is one huge main method, calling just one more benchmark method, calling just one more time related method, and I think this can be greatly improved to have more idiomatic C code. And I think this episode should also show that proper software development always requires iterations. So right here we have a monolithic block of stuff that's being done and it works, but it's just not very extensible, it's not very legible, it can be improved. There's big room for improvement. So let's start today's refactoring by just having a quick look at the software again, just so we see what it does. We specify that we want to benchmark the current disk with 1 gigabyte of test data in the current directory. That's what the dot stands for. So let's test that. As you can see, it took 0.92 seconds to write a single gigabyte, and therefore the write speed is 1091 megabytes per second. And for the random data, so this was testing writing zeros, and this is testing random data. This is taking 3 seconds approximately, so it's writing a third of a gigabyte per second. All right, and all of this is being done in this monolithic block of code right here. And the first thing that stands out, in my opinion, is all these initialization of file pointers and also the allocation of memory. Yeah, and in our main method, I don't think we should care so much about memory allocation, file pointer initialization, opening existing files, and then also closing them and removing existing files. All of this shouldn't be a worry of the main method. At most, the main method, in my opinion, should care about the arguments, the input arguments. Currently, there are 2 arguments expected, the number of gigabytes and the directory to test, representing the disk. And that's it. And then the main method should call, in my opinion, the actual program. So the main method acts as just the command line interface of the real program. And the real program should be separate from the main method. So what we need to do is we need to create a new function, and let's first not return an error code. And let's create that function and call it benchmark. And we benchmark a number of gigabytes. And a disk path. So that's a character pointer, a string path. All right. So that should be the interface of the actual thing that we're doing, that tightly corresponds to how we're actually calling the program. We are inputting the number of gigabytes and the directory to test it with. So this is the benchmark method that we are using. Now, let's see if we can just copy all of this into the benchmark method. Now, the benchmark method is obviously still very monolithic, and we have to do some cleanups, but this is already a small improvement. We just have to call the benchmark method here with the number of gigabytes, and here we have to extract the number of gigabytes here. So this is still very monolithic, but of course we're going to iterate on this and improve it to Idiomatic C very soon. So we're passing the number of gigabytes here, Let's also rename this. It's numGB, of course. And the second argument is the path that we want to test this on, and this is here. So let's remove that from the benchmark method and call it here, disk path. And this already looks a lot cleaner, at least if we just look at only the main method. So the main method is checking the argument count, and then it's taking the arguments and benchmarking based on the arguments. And that's already a big improvement in my opinion. So the next issue that I want to fix is still this block of code here is very monolithic. So what is it doing? Let's have a look. So everybody is on the same page here and everybody can follow along. So this is the entire benchmark method. And the benchmark method effectively defines a file that it wants to test with, for example, for writing the 0 files. Then it opens that file. Then it opens the related file pointer or the related special file as that is the source file for our test data. In our case, it's def0 for unlimited zeros and def_random for unlimited random numbers. And then it's performing a test and printing stuff to the console, and then it's removing the files, and then it's closing the file pointers and freeing the memory. So there's so many different things going on here, and this totally should not be in a single method. This method has so many responsibilities that just shouldn't be the case. All right, so what is the first thing that we can do? First, aside from improving just the code itself and making it more shorter and more succinct, we should also check the user's inputs. We should catch errors early. So let's check here if numGB is not, or no, if it's equal to 0, then we can return this method. Now, of course, this is just another block of logic here that might disturb any future programmer reading this. And it's increasing the size of the method, but this is catching an error early. Now, this block doesn't look so nice. And of course, if the user, now, let me just compile this, gcc benchmark.c, output is benchmark. Oh God, we have to fix some compilation errors. But if the user is going to call the software with numGB equals 0, and the method just returns, I don't know if that's good behavior. Maybe you could say it's good, because if the user specifies 0 gigabytes as an input, then maybe nothing should happen. But what definitely should not happen if the user specifies invalid inputs is that memory is allocated. We should never allocate memory in case the user inputs invalid stuff. And also we should not open file descriptors, because as soon as we start opening things and allocating memory, of course that stuff must be closed again if you want robust software and good quality software. So for example, imagine malloc executes on, imagine fopen executes and fails because the input is invalid. Then at this point in time, malloc has already executed, and then fopen fails, the function will exit somehow, but the buffer is already allocated, yeah? So in case of every single error, you must make sure that the data you allocated is deallocated again. And that's what makes C so tricky. In other programming languages, they solve that using exceptions and then cleanup functions, catch clauses, finally clauses, and stuff like that. We don't have that in C. And that's what makes C very sensitive to those errors. And you need to pay attention to properly doing those things. So let me just compile again with all and even extra warnings and debug flags enabled, just so I get all the warnings for better troubleshooting. So let's check the first error. Conflicting types for benchmark have void. Conflicting types for benchmark have void. Of course, down here, no, I am calling the function. Then the function is defined up here. And then there's another benchmark function which we just declared. Of course, this benchmark function is different from this down here. This function down here should be called benchmark. That's the main function. And then this function here should be called maybe process benchmark. And this is an internal function. So this benchmark function takes care of everything, allocating all the stuff that we need and opening all the file pointers and removing everything afterwards and closing all the file pointers and deallocating memory. And internally, it's then running process benchmark to perform the actual logic. So how do we do this? A benchmark, as you can see, is quite complex. It's allocating a buffer, it's allocating files, it depends on the source file, and then everything is removed. And worst of all, we perform two different benchmarks in our code. We perform a 0 benchmark with only 0 bytes and a random benchmark. So this should be separated out. We should run two separate benchmarks, but they should be executed via a single method call. All right, we'll do all of that. Let's just have another look at the compilation. What errors persist here? Disk path is undeclared in line 40. Line 40 is this, and this is undeclared because, yeah, right, the input path is called path now in this function. So we need to fix that. This is path, and this is path. And is there any other usage of disk path? I don't think so. No, there's not. Okay. Let's check the warnings and errors. And what is there? Gigabytes undeclared, of course, because we renamed this to num gigabytes. Num GB. Okay. I think now this should be fixed. And now, as you can see from these few small changes which we did so far, already a lot of errors and warnings occur, which were not there before. Error: too many arguments to function benchmark. Number of gigabytes P0, FP disk 0. Too many arguments. Why is that too many arguments? Of course, because this is now a recursive call, which we don't want. It should be run or process benchmark. Okay. Now, now the function the file compiles without any warnings. Now everything's perfect according to the compiler. But it's not perfect according to our own standards because, as I said previously, this number of gigabyte check equals 0. This can be improved already. It depends on whether you consider this valid input or not. You could give the user an output, a printf statement saying number of gigabytes must be non-zero. I consider this an error in my case, so let's do an assert statement that checks the number of gigabytes. And if it's 0, it's going to fail, of course. So let's just explicitly write here number of gigabytes is not 0. And then that's a hack. We can say that number of gigabytes must not be 0. Because now the assert statement, which is a macro, is going to fail in case the number of gigabytes is equal to 0. And then it's going to print the entire argument that was given to it as a string. So let's test that. We need to, of course, include assert. And let's test. Now it compiles without a warning. Let's run benchmark 0 in the current directory. And as you can see now, we have a proper assertion error. Number of gigabytes is not 0, and number of gigabytes must not be 0. So this already tells the user something about the error, which is very useful. You should not just return. Of course, you can also define error codes, but I find this assertion failure here very nice, especially as long as you haven't allocated any memory. And currently we haven't allocated any memory here. So this is a simple assert that checks the validity of our number of gigabytes value. And then we can create another assert for the path argument, which must not be null. So we can do path and path must not be null. So this is in case somehow the function is wrongly used. In this case, it's not going to happen because argv2 is only going to be passed if the argument count is 3. So that always exists and is always a string. So it's actually from a bash shell perspective impossible to give a null value here. But we don't know, maybe one day that function will be used as a library function, and then, of course, the path given can be null. So we have to check. All right, and let's compile and benchmark 1 gigabyte in the current directory, and let's see if it still works. And it still works, apparently. Yes, good, very good. And let's also check just to be sure that the files that were used for testing were deleted, and that's also the case. All right, so that looks already quite good. So we have 2 assert statements that are guarding the benchmark function. So we know that here it is very unlikely that the allocations fail. Well, no, the allocations will not fail. Right, the path is at least not null. Of course, it can still be some invalid string with weird characters or some path that just doesn't exist, but we will take care of that later. First of all, I would suggest to split up all of this stuff into a separate method that takes care of one benchmark. And as you can see here, there are 2 tests running and both of them do effectively the same. The difference between them is just the source file that was used. So this right here is effectively the difference. One uses source file def0 and the other uses source file def random. So let's create a new method, void and that is an initialize benchmark function. that takes as an input the source file, character pointer source, source path. Yeah. And it takes as input, what else does it take as input? So it's opening the source path here, and then it's writing to a target file. The target file can be actually a single fixed file that we use for all the tests, so we don't even need to specify it here as an input argument, because it will be opaque to the user anyways. The file will be hidden. It will exist only as long as the test runs, but then it will be deleted automatically. So it doesn't need to be an input argument to the function. We can just hardcode the test file name. And what is important though is what else is important? Actually, everything else can be fixed, I think. Yeah, so the benchmark actually only depends on the source file path, and we of course want to know how many gigabytes are written. Well, actually, no, the target. No, of course, no. The target path is also important because we have to know which disk to test. So source path, destination path, and then the number of gigabytes, num gigabytes. And that is going to initialize a benchmark as follows. Let's copy all of this stuff here into the init benchmark, and we will, inside this method now. No, let's undo this. Let's do something even nicer. This method will return a benchmark structure. Let's call it benchmark. It will return a pointer to a benchmark structure. And effectively, a benchmark consists of a source path, a destination path, and a number of gigabytes. So let's define a benchmark structure here. Type def struct character pointer, or maybe even a file pointer. Yeah. Source, destination, source dest, or maybe even source dest or dst. Yeah, that's nice. And int num gigabytes. And that structure is called benchmark. Now down here we initialize a single benchmark rather than mixing up two different benchmarks. And that benchmark object is, or that structure is a structure that contains only initialized file pointers that can be operated on. So let's do that. First, we need to allocate. Yeah, let's just copy the stuff for one benchmark. So first, we need this part here. This is creating a string that is actually the source path. Oh, wait. No, we initialize the benchmark with the source path. The source path is this down here. This path is the source path. Okay, so that must be this line. And it's not P0 anymore. Let's just keep it for a second as P0, but we'll rename it soon. The other one can be removed. Then this is just for initializing the benchmark, or maybe not init benchmark, but create benchmark. So this is creating a benchmark. Then pdisk0 0 bin, this is defining the target file path, which is taken as an input argument to create benchmarks. So this can stay here. But then the destination file pointer must be constructed inside create benchmark. So let's do that. Okay, so we need to open the source path. We need to write to the destination path. And then the number of gigabytes is an integer. That's fine, no difficulty there. So this is creating a benchmark so far. So let's allocate space on the heap for the benchmark object. To do that, we have to use malloc. So this is going to be a benchmark pointer. pbench is equal to malloc, and we just use size of, the size of operator, size of benchmark. We allocated the size of a single benchmark. Then we do pbench source. Source is equal to not P0, but P source. Well, let's just call it, P source. And fpdisk0 is pdest. That's the destination. pbench destination is equal to pdestination. Okay, so basically we're just setting fields on our structure, and then also we need to set the number of gigabytes equal to number of gigabytes. And this can then return a valid object where we know that the file pointers have been created. But how do we know that the file pointers have been created? Because those can fail. So here we need to do if this I think we can do if this is defined, if psource is not null, then we return, no, wait. So here we have to make sure that fopen worked. Yet now we can check if psource is not null, then we do something. Or we can even make it more succinct. If psource is equal to null or pdestination is equal to null, then actually we want to terminate the entire application because something just went wrong. So maybe we should use assert again. So psource. Well, but maybe assert should be used for programming errors. But the source path and destination path thing can also depend on runtime. It's actually runtime behavior. Do the files have the permissions to be opened and written to, and things like that. So maybe we should just return we need to somehow tell the user that opening the file was wrong or didn't work. Printf. We can print to standard error. Source or target file is not readable or writable. But also that wouldn't be so helpful because the program just continues running. We can return null. How about that? Return null. So that means that creating a benchmark failed. All right, let's just consider this a benchmark. This is the create benchmark method. If either file cannot be opened, then we return a null benchmark. So if the benchmark is not null, then we know it's valid. Returns a benchmark can be null. Returns a valid benchmark, otherwise null. Something like that. Some documentation is always helpful. All right, and then down here we can say we want to create a benchmark, create benchmark for the source file. The source file is now def0. The destination file is the file name that is created here by concatenating strings, pdisk. Or actually, we don't even need to separate destination files. We can just do the following. P-destination file, then string, then this is allocating space for a destination file. Let me just remove all of that. That's just unnecessary. Also, we don't need 1,000 characters. Let's say 300 should be sufficient. This is now concatenating the given path with the destination file path. But what was the given path? Ah no, this is copying the path into the destination file, of course. Into the destination file string, and then this is concatenating zero to that destination. And actually, I don't like this method. This means I should create a separate method here that returns a character pointer, create destination path, a destination file string. And the input is the overall path that user inputs. And that's already it. So let's copy all of that. We allocate new memory for that string. And then we concatenate it with a file called test bin. So that's basically a method that defines or that returns a string representing the test file or test's target file path. Okay. So now here we are allocating memory and we are copying something into something. we are copying the given path into our allocated memory. And then we are concatenating this. Of course, now this is annoying because this requires us to clean up the allocated memory again. So we make this the responsibility of the caller. Must be freed. Return value must be freed. Okay, done. And now we are creating a benchmark for the given source file path. This is the source file path. This is the target file path. And actually, we shouldn't take care of this here. This can be taken care of in the create benchmark method, the creation of the destination file path. So here in the create benchmark method, now we open a file. We don't open the destination path. This must be the destination dir directory. So we must make explicit that this is a directory. Dir, and we don't open this because this is not a file yet. This is a directory. Now we must make sure that we create the destination file string here. So let's do that. Destination file is equal to create destination file string for the destination directory. Destination directory. And then we open the destination file. And after using this string, now we need this string only for using it. We can already free it. Free destination file. All right. So this is creating a benchmark now, and this is working. This is just the initialization of the benchmark object and throwing away all the inputs that we don't need. Or, I mean, deallocating the memory already that we don't need, that we never need anymore. Okay. So here we can now create a benchmark for the given path with the number of gigabytes. And this is now a neat method that returns a benchmark structure. P benchmark 0. This is now the benchmark that tests based on the 0 special file, that tests writing pure zeros. Now we can do the same thing for our second benchmark, for the random bytes. That's taking as input def random. All right, that looks good to me. And then we have to process the benchmark. And here we can printf, that's fine. Then we process the benchmark. Now we don't need all these special parameters here anymore. We just need to give this function our benchmark to process based on p benchmark 0 and then p benchmark rand. All right, and then let's fix up the run benchmark or process benchmark method. So it takes as input gigabytes. We can replace that already with number of GB. No, we cannot. We have to replace that with benchmark arrow operator num GB. Let's see if this works. Yeah, I think it worked. So this looks good. It's accessing the number of gigabytes. And of course, this needs to be a benchmark pointer object. Let's call it benchmark for now. Actually, it should be p benchmark to make sure to explicitly state that this is a pointer, but I don't know. I don't really know if this is a good practice to do always. Let's keep it that way, and in the end, let's unify it across the code. So we get the current micros, we get from the benchmarked object now the number of gigabytes. This is now performing the actual benchmark logic. This right here is allocating a buffer. Now this is already dangerous. Should we allocate a buffer here? This is the buffer for the reading of chunks. Okay. Oh, and I see that we forgot even cleaning up that buffer. We should, of course, clean up that buffer at some point, latest here, ideally here. So this is reading the chunks, then it's reading it for thousands of times, performing the actual benchmark, then stopping the time. Maybe I should free in the end to not impact the measurement. And then it's printing out the result. Now, as you see that still this is mixed up with the actual code created down here. So this is printing out testing zeros, then it's processing a benchmark, and maybe the result should be a return value. But inside this method, there's a printf. So the printfs are interleaved throughout the code, which shouldn't be the case in my opinion. We should make this a return value. And the return value contains two variables, delta times seconds and speed. And for that, we can create a new structure, type def, struct, and both of those values are floating point numbers, seconds and speed, or megabytes. Yeah, no, seconds and speed. And that is the benchmark result. Speed in megabytes per second. Okay, let's try and see how we can use that to refactor this a bit. So down here we can now create a benchmark object and return it. Or we use an out object up here. So that's a benchmark result and it's written into here. Or maybe even better, but I don't know exactly. Maybe what if the benchmark itself contains the result? And once the benchmark is run, we can read from the benchmark's result. Let's try that. Benchmark result, result. And that's of course a pointer, p result. And that means in the benchmark creation method, we need to also create a benchmark result. So I really want to tie all the creation and allocation of memory together into one thing. So the benchmark result is created here. P results, and it's the size of benchmark result. And then down here, or here we can check, or p results is null. And this can be even shorter. This can be p source, if not p source, or not. I don't know, this is more explicit. And then on the benchmark object we set the p results to p result. All right. Okay. And I'm not even sure if we really need to. No, we don't even need to allocate space for a benchmark result here. If we don't store the result as a pointer. So we can keep it even more simple by just saying that the benchmark result is not a pointer in here, it's just a part of the structure. And this way, the benchmark result is part of the creation of the actual parent benchmark and is already allocated here, and it's destroyed and freed once we free the benchmark. All right, that looks good to me. Now we process the benchmark here. Maybe let's do this. And then we calculate the past time here. All of this can be a separate. All of this time calculation can be a separate method as well. But I think it's relatively fine. We're reading and when we're reading the source and writing to the target, then we are stopping the time up here. We are allocating the memory for the buffer. That's the thing that is bugging me here. Where do we free the buffer? We free it down there. But of course, if any of those methods here throw an error or somehow cause the application to interrupt, well, there's no proper freeing here. But I think this is now still relatively succinct. We don't have any nested if statements. Yeah, let's keep it like this for now. I definitely want to pull the printf statement out of this method and the time calculation. But yeah, the start time micros and the end time micros, I mean, that's fine. So delta time micros, yeah. Okay, let's create a new method that's returning a benchmark result. Or that's setting a benchmark result. Void set benchmark results on the benchmark p benchmark based on the delta time seconds and the speed. And what it's doing is it's accessing p benchmark and setting benchmark results equal to a new benchmark result with the values seconds and speed. Okay, and of course those two are floating point numbers. Now we also need, of course, to perform those calculations there. What's the speed? No. What's the speed? The speed is the size divided by delta times seconds. Wait, the speed must be calculated inside this. And the size is this up here. It's the data size that is being tested. And maybe the size should be cast to a double. What's the biggest floating point number? Biggest float in C. I think that's good enough. Because here we are using a long and here we are using just a float. This could be a double. Double size divided by delta times seconds divided by this, by all of this. This is a float. This could be double size. Or long size. And the long size is divided by delta time seconds. No. Wait, what's the speed? Let me just rethink this. We are setting a result on a benchmark. We have a size and we know how many micros it took, And the speed is the size divided by the micros. That's the number of size in bytes. Micros in micros. So that's basically bytes per microsecond. Bytes per microsecond, is that the same as gigabytes per second? Bytes per microsecond is the same as kilobytes per millisecond, and that's the same as megabytes per second. It's the same as megabytes per second. Yeah, that's the speed in megabytes megabytes per second. And we can set that here, speed megabytes per second, and let's also make this explicit up here such that we don't need a comment. Oh well, no, let's keep the comment. Let's keep it explicit. So this is setting the result, this is the speed, this is the delta times seconds here. Now we need to convert the delta time also into seconds to make it nicer. And let's make this a double just to make sure that we don't have stupid limitations of the measurement. I mean, the seconds and the speed should never be such large numbers. Oh no, it can be floating point numbers actually, but the computation should be done using doubles at first, because the size is measured in bytes and this is measured in micros. So those can be very large numbers, but the division can be small. Okay, so let's change that to a float. That's now very efficient, not wasting too much space. And that's setting the benchmark result on the given benchmark pointer. Now the last thing that is missing is here we have to now set the benchmark results on p benchmark. I will rename the benchmark to p benchmark in a second, for the given size and the given delta time micros. And we can free the buffer up here, set the benchmark result, and then say bye. And this printf statement here can be extracted into a separate method that's called void print result. And it's taking as input a benchmark result. So it's printing took so and so many seconds from the result dot seconds. Yeah. And the result dot speed. Okay, we can print the result later. We can print it later. And I know I must also unify my method names from the underscore notation to and camel case to something that is aligned with each other. So we are processing the benchmark here. We are freeing the buffer. We are allocating a short temporary buffer. That is fine. We're freeing it here. Yes. That is fine. And then we are setting the benchmark results here and saying bye-bye. That's it. All right. And then we can do the following. In this method here, we printf testing zeros, and then we print the results of our p benchmark 0. And down here we print the result of the other benchmark, p benchmark rand. And now comes the fun part, cleaning up all the mess, removing all the file pointers. But before that, let's check the compiler. I'm sure it's full of warnings. errors. Okay, of course. Yeah, and of course it doesn't work because down here we are freeing a lot of stuff that the method doesn't even know exists. So we need to create a new method that is not create benchmark, but destroy benchmark. So that's the opposite of that constructor method. It's a destructor method. So let's do that here. Void destroy benchmark. We are given a benchmark p benchmark. And then we are accessing the individual fields of the benchmark. So we are accessing p's benchmark source. If the benchmark source is not null, it shouldn't be null, of course, because we have properly created it. But then we free pbench source. What's source again? Source is a file pointer, so that's why we need to no, we don't need to free it. We need to close it because it's opened in the benchmark creation method. It's opened here. All right. Okay, so if the source is not null, then we close the file. If the destination is not null, then we close the destination. If the number of gigabytes is just an integer, we don't need to worry about that one. Then the results, if the result, pbench result is not null, then we free it because that is allocated space. That is an allocated buffer. No, it's not. It's not. It's part of the structure here. It's just a structure stored in our parent structure. So we don't need to free it. This is freed as soon as we do free pbenchmark. And that is destroying the benchmark. Okay, that's already very fine. As you can see now, the freeing of memory is very concise. And we can do it down here. Destroy benchmark, p benchmark 0. And then let's do the same thing for the other benchmark, p benchmark rand. Now the only thing missing is the removal of the test files here. And I think that should be done in the method that processes the benchmark. And that means or where should it be done? Where should the destruction or the removal of the test files be done? Where is the test file used? It's used in, well, here obviously. Here we're reading or we are writing something to the destination file. As soon as that is done, we can actually not only free the buffer, but also free or remove the destination. What is the type of the destination? What is it? We don't know. We don't know because it's part of the benchmark. We need to refactor this method still. So benchmark chunk size is 128. That's fixed. Since it's fixed, let's put it at the top. Then the reps depend on size and chunk size. That's fine. Reps is repetitions. Then we are allocating new space. Then we are getting macros here, running the process, freeing the buffer, removing the destination file. The destination file is coming from benchmark. P benchmark source and P benchmark destination file. Now let's rename this to P benchmark here. All right, and if we want to take this to the next level, then we should take the allocation of this temporary buffer for the benchmark. We should take this into the benchmark as well. And of course, this should never be allocated by the user. This should only be allocated by, the structure should only ever be created by the create benchmark method. And that's what it's used for. It's a constructor. So this can be a void buffer for running the benchmark. Let's call it buff. So instead of initializing it here, we initialize it in create benchmark down here. And we do the following. We allocate space for the benchmark, and then we also allocate space for the buffer. So void pointer pbuff is equal to malloc 128. And then we set, of course we have to check if this is, if pbuffer, if pbuffer is null, of course, then let's attach it to this if statement, which is getting a bit long, but still okay, but shouldn't get any longer. Or actually, now we can make it a bit shorter. So if not p source or not p destination or not, what else was there? P results. I need to remove the p results again, which makes it a bit shorter again. No, then we can keep it like this. Or no, let's do it. P source, if not p source, so if it's not null, or not p destination, or not p buffer. So if any of those is null, we return null. And down here we know that those fields are not null. The result, we don't need to allocate it here. P bench buffer is equal to p buff. And let's rename it to p buff here as well. I'm sure there are many name issues now in the compiled code once we try to compile it. So let's see, what were we doing? We were allocating this buffer here, but this is not necessary anymore. We can just read from the benchmark, p benchmark, p buff now, which is the buffer that this test is using, p buff, and then write to that same buffer. Use that same buffer for writing. P benchmark, p buff. And now one more point, the chunk size, we are hard coding it here, but this potentially conflicts or is inviting programming errors here. So we can create a chunk size field on the benchmark. Int chunk size and set it down here. P bench chunk size is equal to 128. And then down here, it's allocating space for that chunk size. And so now we never need to know the chunk size again, so we can delete it here. We just need to properly access it, of course, from the benchmark, like this. So now there's no initialization of memory here. There's just a freeing of memory and removal of the file here, which we can move into the destroy benchmark method now. So you see that this is slowly tidying up everything. Destroy benchmark is happening down here. So let's just free our p benchmark buffer. If p bench, why am I writing p bench here? Well, let's do this, p bench. P buff is not null. Then let's free p bench p buff. Okay, and then we can remove the destination file. Well, here we're trying to free the entire benchmark. We can also check if that benchmark is null, but that should never be null. Except the benchmark creation was invalid, of course, then we return null. So here we can actually check if p benchmark 0 or not p benchmark rand, then, no, this can be an assert. Because this is an exceptional case, this should never happen, because we properly create benchmarks here. So this is a programming error if this happens. So let's just assert this. Benchmark creation failed. Okay. And down here where we are removing the destination file is stored how can we get the destination file name? This is setting the destination, the benchmark result. This right here is aware of the destination file. So can we just remove the destination file? Wait, let me just look up the man page again. And it's taking a constant character pointer path name. So this requires the string, which we have thrown away already. Get path name from file C. I don't want the absolute path name, I just want the file name from the file pointer. And of course that doesn't necessarily exist. So how do we delete the test file? What's the last place where we know about the file name of the destination file? We definitely know about the file name when creating the benchmark itself, of course, but then we are converting it to a file pointer, but maybe we should also create a character pointer. That's the destination file name here, just so we can make sure that we remove it later. And we of course need to update create benchmark now. So let's store the destination file name, which is this, also on pbench destination file. How did I call it? Destination file name is equal to this destination file. And then we don't free it. We free it later. We free it in the destroy method. Let's go to destroy then. And down here we do the following. We do source destination file name. If it's not null, then we free the file name. Destination file name, just like this. And then we can remove the destination file name. No, we have to remove the destination file name first. Or we have to do it inside this. Oh, that's even better. That's so nice. I love this. So now we have this really nice cleanup method. It's cleaning up the source file pointer, the destination file pointer, the destination file name. It's actually removing the file and then freeing up the memory allocated for the file name, and then it's freeing up the temporary transfer buffer, and then it's freeing up the entire benchmark object. Is there anything else here? Well, the number of gigabytes does not need to be freed. The result does not need to be freed, or is part of the freeing of the entire benchmark buffer pointer. And the chunk size doesn't need to be freed either. When we create a benchmark, now we must make sure that we still set all of the flags or set all of the members. So we set the source, destination, number of gigabytes, p buffer, chunk size down here. I think we have it all. Benchmark result is kept null as long as no benchmark result exists. Okay. So let's see where create benchmark is created. It's here. We create a benchmark, then we print that we test our benchmark. Then we process the benchmark, and now we're printing the results. Aha, bug caught. Results. And we print the results here as well. Results. And then we destroy both of the benchmarks. And I think now the code looks much more pleasing. Now first, before we test anything, I want to make sure that all of the method names are aligned. So let's use the lowercase notation. No, the underscore notation. Set benchmark result. Where's set benchmark result even used? Set benchmark. Ah, there it is. So let's rename that one. And let's also rename those calls here, print results to print results. And now let's see what happens when we compile. Yeah, for sure it doesn't work. Unknown type benchmark. Did you mean benchmark? Ah, I had a typo. I typed benchmark. So let's search for benchmark and fix it up here. Benchmark. Now in function destroy benchmark. No, let's start with the topmost error. Oops. Okay, delta time micros is undeclared in set benchmark result. Delta time micros is undeclared. Okay, that should be simple to fix. Delta time, where is it used? Here. And it's just, we can simplify it to this. Awesome. Seconds. Now it looks much better. Okay. Now, what's the next error? The next error is in function print result, benchmark result has no member named speed. Yeah, because we renamed it to speed underscore MBS. What was the line number here again? 39. So let's go to line 39. It's this line, and here we have to access speed MBS. Now, what's the next issue? Let's compile again and see. Benchmark undeclared. Did you mean uppercase benchmark? No, I don't think so. It's in process benchmark line 44. Ah, it's P benchmark, of course. And while we're at it, we can search for all occurrences of benchmark and see if there's any non-P starting benchmark. There should never be, I think. No, looks fine. Okay, and let's compile again. In function process benchmark, error chunk size undeclared. Line 50. Line 50. Error chunk size is undeclared. Chunk size comes from P benchmark. Chunk size. Same here, P benchmark. Chunk size. Let's compile again. In process benchmark, P benchmark undeclared. So there's a typo somewhere. Yeah, P benchmark fixed. Let's check. In function process benchmark, error incompatible type for argument 4 of f write. I passed in a file. But what is expected? A file pointer. Expected file pointer, but argument is of type file. Didn't I pass a file always? Isn't this a file pointer? Wait. This is a file pointer, isn't it? Or should I do this? I think I have to do this. Not sure, let's try. No, still the same issue. File pointer, but argument is of type file. P benchmark destination. How is that possible? No, I think I have to do it like this. So this is the source file, this is the destination file. No, I was looking wrongly at the logs. The logs are much shorter now. Now this is my last command and only this is the remaining errors. So in function destroy benchmark, error destination undeclared. Remove destination. Line 105. Let's go to line 105. Remove destination. Of course, it's undeclared because it is inside P bench destination. File name. Okay. And now there's one last error, and that is P benchmark undeclared. Did you mean benchmark? First use in this function, destroy benchmark line 113. 113, 3 P benchmark. And here it's called P bench. Okay. And there's one more warning. In function create DST file string. Warning, control reaches end of non-void function. So let's have a look at line 65. And I'm promising to return a character pointer, but I'm not returning anything. So let's return here p destination. Okay, and now it's compiling without any warnings. The code is looking much better now. It's super nice, super idiomatic. See, as best as I can possibly write it. Now we are creating a benchmark. We're constructing a benchmark object that is responsible for managing all the memory and file pointers and everything related to the benchmark. Then we process the benchmark, and then we destroy the benchmark. And we never need to worry about missing allocating stuff ever again, because we know it's properly destroyed in the destroy method down here. Now we have created those two types. Yeah, and we have done so many interesting changes now. Let's see if it still works. And it doesn't work because the assertion p benchmark 0 one assertion failed. Benchmark creation failed. P benchmark 0 or p benchmark rand. Why is that? And we must make sure, of course, that def 0 and def random really exists. Let's cat def 0. This one definitely exists. And cat def rand. Oh, this is probably the issue. So as you can see, this is more, the assertion is very good for developer troubleshooting because it will fail the application. It will not cause any weird behavior. And then we can just, based on this assertion, we can check what's wrong. So, no, it's random. And of course, it's random, and I properly used it in the code. So that's not it. It's something inside create benchmark. And only afterwards the assert failed because one of the benchmarks returns null. So let's go here and check when it returns null. And I would say we should compile. Let's check one more time. Yeah, assertion is triggered. So let's hop into GDB for the benchmark and put a line break in line 83. Not a line break, a breakpoint in line 83. And let's run with one and current directory. Let's make it more explicit. Home, Daniel, projects, disk, benchmark. Is that the directory? Yeah, okay. And now we can find out what the issue is. We can switch to the source layout. It's not available. Let's restart it. Layout source. Break 80. Which line was it? Let's look for it here. 80 something. 83, right. And let's run one home Daniel projects disk benchmark. Program received sick abort, so something seriously went wrong. Let's have a look. What caused it? It's of course the assertion, but that means that something else failed. That was not caught by us. What could it be? So we did not reach this return statement here. Refresh. Let's print a couple of variables. pbuff. It doesn't work. We have to probably create a breakpoint in somewhere else. GDB benchmark, then run home Daniel projects disk benchmark. Why doesn't this work? Again, layout, source. Let's put a breakpoint aggressively into our create benchmark method. Line 71, break 71, and run and see what happens here. Process exited normally. Why is it not using our breakpoint? Create benchmark. What? Huh? I have to say run with 1 GB in the current directory, of course. So now I can print the source path is def0, print the destination directory is dot, okay. No, I think that's not correct because the bash shell should expand it, and now we're in the debugger, which doesn't properly do it. Let me quit. Layout, source. Let's put a breakpoint in line 71, break 71, run 1 GB of test in this directory. Now print destination directory is now properly set. Print number of gigabytes, properly set, and print the source path is also properly set. So let's step through this. So here we have now allocated memory for the benchmark. Now let's step, 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 step. So all of this works so far. Print the destination file. It's also a valid path for our destination file. Next. What's this? I try to open the destination file, which is a character pointer, it's a string, but I need to open. Oh no, that's fine, that's fine. I was confused. I was confusing strings and file pointers. Let's try. Print p source is fine. Print p source, print p destination, print p buffer. All of those work. So let's see where the problem is. Return pbench works. Now there's another benchmark creation. All of those work. Probably it's just my assert statement that is messed up. Yeah, of course. That's the case. Oh God, it's always the simple things. Of course, we have to assert that benchmark 0 is not null and it's not random. This is not like an if statement where we check, is it not null? If it's not null, then continue. That was the logic I had in my head but we have to assert that both of those are non-null, and now it should work if we compile. Testing zeros works, testing random numbers works, and guys, this is how you properly write idiomatic C, or, well, maybe it's not perfect, yeah, but in comparison with the starting code, with the code that started today's episode, this is now much cleaner because we separate out the construction and destruction of the benchmark object right here. And we have separated out the command line interface with the actual invocation of the library. So the main method is now only taking care of the command line interface. It's calling the benchmark as simple as possible with a number of gigabytes and a disk path. The benchmark is basically the manager for everything. It checks that the inputs are not null, and it's creating benchmarks as structures in memory that are automatically basically managed by the library that we just created for creating benchmarks. And then it's processing the benchmarks, printing out the results of the benchmarks, and all of that is encapsulated in nice methods. And then it's destroying the benchmarks. And so we effectively separate out a entire manager method that does everything, creator methods, the constructors, the performance, or the processing of the benchmark, and the destruction of the entire benchmark. And all of this leaves us with a completely clean directory. The benchmark, there are no leftover files here because everything is deleted as part of destroy benchmark, and this is now proper, ultra nice, super clean code. For sure, some of you will find further improvements. Please write them all in the comments. But I definitely learned something this time in this episode, writing better and more maintainable C. If you enjoyed this, stick around, subscribe, and see you next time. Bye bye.